Hi there, mathematicians. Let's get started with the last section of Unit 4, 4.6, Similarity and Transformations. Alright, so at the top of the first page, where our explorations are located at the beginning of every section, we see our essential question. When a figure is translated, reflected, rotated, or dilated in the plane, is the image always similar to the original figure? That is our essential question for 4.6. So, two figures are similar figures when they have the same shape, but not necessarily the same size, and we can see that illustrated with our two triangles here. Triangle ABC is similar to triangle EFG. Okay, so now we see here a similarity statement. In previous sections, we saw congruence statements. So when you're dealing with similarity, it's a new symbol. You take away the equal sign, and you just do the squiggly. So you have triangle ABC is similar to triangle EFG. And again, order of letters matters. So vertex A will correspond to vertex E. Vertex B corresponds to vertex F. Vertex C corresponds to vertex G, which means corresponding angles are congruent. So A is congruent to E with similar shapes. All your vertices are congruent. The sides, however, are not congruent with similar shapes. Instead, they are proportional. So length of AC is proportional to length EG, and the same proportion for BC corresponding to FG, and AB corresponding to EF. Alright, so the explorations allow you opportunities to use your geometric software on your calculators. So once again, getting more and more familiar with your software on your calculators to explore ideas presented in the textbook would be a really great idea for you to start using that more often and learning more and more about your calculator and how it can help you discover ideas in geometry. So you have a dilations and similarity exploration, and then you have rigid motions and similarity. Remember, rigid motions means to maintain length and angle measures. Alright, let's get into the topics of section 4.6. So it looks like in 4.6 we want to perform similarity transformations, and we want to be able to describe similarity transformations. Make sure you read through the text, make sure you understand all the vocabulary. All the vocabulary that is important to note in your journals is going to be highlighted, and especially if it's new vocabulary, it's highlighted for you. If there are words within the text that you do not recognize or know, you can look it up in the glossary because it's likely that it has already been presented in an earlier section. And then we have example 1 where we're performing a similarity transformation. Graph triangle ABC with these vertices and its image after the similarity transformation. So here we have a composition of transformations. The first transformation is a translation, so that means we're going to slide 5 units to the right and then slide 1 unit up. And we can see that by looking at triangle ABC is the pre-image, and so every vertices translated 5 to the right and 1 up, getting us mapped onto A prime, B prime, C prime. And then your second dilation is a center about to -1. So remember, you have to follow the rules that you learned in 4.5 when you have a center of dilation that's not at the origin 0, 0. It follows a special formula. So let's see what that formula is. Okay, so let's see what kind of numbers, when we plug them into our two different rules, will result in our images. So we've got our pre-image A, first transformation will be a translation of 5 to the right, so we add plus 5 to every x value of vertex ABC, and add 1 to every y value for vertex, the pre-image of triangle ABC, resulting in our image A prime, B prime, C prime locations. Then we take these image values for A prime, B prime, C prime and plug these numbers into the next transformation, which, remember, if it's a center not at the origin, it has to follow a special formula. And our scale factor is 2, and that's noted in our rule. So the scale factor 2 gets multiplied by the x value of A prime minus 2, which is the location of the x value for the center. And then that gets computed, so 1 minus 2 is -1. -1 times 2 is -2. And then plus 2. This plus 2 came from the center value 2 and results in a 0 value for A double prime. And now for the y value, you're going to take your scale factor 2, which again is the scale factor given, times 2. This 2 comes from the y value of A prime location. So 2y minus the y value for the center of dilation. So here's your -1. So 2 minus -1. That results in a plus. So 2 plus 1, which is 3. 3 times 2 is 6. And then 6 plus the -1, which again is the y value for the dilation. So 6 plus -1 results in +5. So you do that same rule for each of the vertices, taking the prime coordinates, plugging into the formula to get your double prime locations. We also see step 2, step 3 explained in the text. The text didn't show you the formula, so I'm providing the formulas here to help you with each transformation. And then you can try 2 on your own. The examples for monitoring progress, you have a rotation of 90 degrees first and then a dilation. And then for number 2, you have a reflection of the x-axis and a dilation with center not at 0, 0. So these are really great ones to practice. This one had a center dilation at 0, 0, which is a little bit different than when the center is not at 0, 0. So definitely practice both of those, and we can clarify anything in class tomorrow. All right, so the next page we have performing composition of dilations. So this is where you have a dilation and a dilation. So this is another great example for your dilation practice. Again, center is not at the origin for either of these transformations. So it requires the really long formula, which this time the textbook is providing the lengthy formula to help you see the solution. And it's all worked out for you here and with a picture. So make sure you capture all of these ideas in your journal and make sure you understand how to do each of these examples. And then you have your monitoring progress examples at the bottom with numbers 3, 4, and 5. Number 3 will be an easier one to try because the center is at 0, 0. When you have a dilation at the center 0, 0, they are definitely easier than when the dilation center is not at the origin. So definitely try all of these. Number 3 is easier than numbers 4 and 5. All right, so when we're describing similarity transformations, example number 3, describe a similarity transformation that maps trapezoid PQRS to trapezoid WXYZ. Okay, so when we're comparing trapezoid PQRS to trapezoid WXYZ, it looks like they do not have the same orientation. And we can see that based on choose any side. Probably the easiest sides to compare are going to be sides QR compared to side XY. And you can see that QR is falling from left to right, and XY is rising from left to right. So they do not have the same orientation. So when you're thinking about how to map trapezoid PQRS onto WXYZ, you would definitely need to do a reflection across the y-axis. And when you see that, you should get this shape here. So Q prime, P prime, S prime, R prime. And now the orientation looks similar to our trapezoid WXYZ. Now it still doesn't look like it's going to be the same size, so obviously after the reflection it's going to undergo another transformation, and in this case, since it's reducing in size, it must be a dilation. And then to figure out what the scale factor is, we would want to compare our sides. So you could compare any side to its corresponding side. So let's compare Q prime, P prime to XW. So we count the number of units, so it's unit 1, 2, 3, so a length of 3 compared to a length of 1. So to go from a large image to a small image, you always put the value of the image divided by the pre-image, and in this case our pre-image is Q prime, P prime, mapping onto our image XW. So we have a 1 divided by 3 ratio, therefore our scale factor is 1/3. So if we multiply 1/3 by every side length, we will get the smaller image. So if we multiply 1/3 times every XY coordinate, we will get our P prime, Q prime, P double prime, Q double prime, R double prime, S double prime, which is the same as matching the vertices of trapezoid WXYZ. So, similarity transformation that maps trapezoid PQRS to trapezoid WXYZ is a reflection in the y-axis followed by a dilation centered at 0, 0 with a scale factor of 1/3. And then we have 2 monitoring examples that you can try on your own. And that concludes 4.6. So be prepared to practice these examples. And it looks like we have a lot of options for compositions. So we'll be doing a lot of composition practicing, some translations combined with dilations at center 0, 0, some translations combined with dilations not at center 0, 0, which is going to be a little bit harder than the ones at 0, 0, and then reflections combined with dilation. So any of these combinations we need to definitely practice, so get to know your rules. Also, if you're given pictures, figuring out the similarity transformation that maps, in this case, the blue image onto the green image, and multiple examples there. And then we have determine the polygons vertices are similar. So this is given coordinates. We compare and decide similarity. So we've got lots of good examples to practice our similarity. All right, see you in class.